Today's lesson is inverse functions. So let's start out with what is our learning objective for today? So the learning objective of today is I can find inverses of functions when they exist using algebra by restricting the domain if necessary and switching x and y, solving for y. I can determine if a function is one-to-one by verifying the function and its inverse is also a function. So inverse means undo. So examples to what do I use to undo something else in math? So if I'm adding to undo adding, I subtract. If I'm multiplying to undo multiplying, I divide. If I have x squared to undo squaring, I take the square root. These are a couple examples. So inverse notation in function notation is the name of the function, and it looks like it's raised to a -1 power, but it's not anything to do with power, and I say the word inverse. And by definition, the domain of the function f is the range of the inverse, and the range of the function is the domain of the inverse. Okay, we have a Venn diagram to talk about 3 words that I need to make sure we understand. And we're going to talk about a relation, a function, and one-to-one. We should be really familiar with what a relation is and what a function is. And the new one today will be one-to-one. So a relation is a pairing of any input to any output. A function is a more specific type of relation. This is where each input has exactly one output. If I'm looking at a table, this is where I would say x does not repeat. And if I'm looking at a graph, I would say that the function passes a vertical line test. Okay. Today we're going to talk about one-to-one, which is more specific than function. And f of x and its inverse are symmetrical about the y equals x line, and the y equals x line is the 45-degree line right here. So the inverse and the composition with the function, the result is x, or the other way around, if I take the function first, composition with the inverse, I will also get x. And that has to do with this y equals x line, because I'm symmetrical about this line. So I would add a few more tests. If I was looking in a table, this is where I'd say y does not repeat. And if I was looking at a graph, I would say I pass the horizontal line test. Okay, so the horizontal line. So horizontal line test. All right, so let's do some examples here. Oh, you know what? So let's talk about these vocabularies as a student taking pre-calculus. And what does more specific and moving inside the Venn diagram this means. So any pairing would be students at MacArthur. There's about 2,700 students at MacArthur. So pairing a student with MacArthur at MacArthur is, it doesn't matter who you are, all of you are students of MacArthur. Now, to be a little bit more specific, not every student is taking pre-calculus. So there's a small group of students that are taking pre-calculus at MacArthur. Well, to be even more specific, there are 4 teachers that teach pre-calculus at MacArthur. So to be a little bit more specific is you are a pre-calculus student at MacArthur in Mrs. Stout's class. And if I even wanted to make it more specific, I could talk about what period you're in. So the farther you move in the boxes on a Venn diagram, the more specific it becomes. And the boxes on the inside include the information on the outside, but not vice versa. Okay, so let's do some examples here. So when an original equation is a function, and its inverse is a function, the original function is defined as being the most specific, is called one-to-one. Okay, so we are going to find the equation of the inverse algebraically. To do that, I'm going to replace f of x with y, switch x and y, and then solve for y, and this is the inverse now. Next, I want to state the domain and range of the function and the inverse, and I'm going to plot both the original function and the inverse on the same graph so that I can see how they're symmetrical about the y equals x line. Okay, so I'm starting out with my function. My function is f of x equals the square root of x plus 3. So the first step says replace f of x with y. So y equals the square root of x plus 3. Next it says switch x and y. So I'm going to switch x and y. So x equals the square root of y plus 3. And the final step says solve for y. So solving for y is under a radical, so I need to undo the radical. So the inverse of a radical is squaring. Whatever I do to one side, I have to do to the other side to keep my equation equal. So now I have x squared equals y plus 3. I'm going to subtract 3 from both sides. So I get x squared minus 3 equals y, and my new y is my inverse. So I replace y with the inverse of the function equals x squared minus 3. Okay, so I'm going to plot these. Now, I could plot this directly if I want to with my transformations, or I can start with the parent function. So I'm going to start with the parent function, and I'm going to plot the original function first. I'm sorry. So the original function is f of x equals the square root of x plus 3, which is the square root parent function. So the square root parent function looks like at x equals 0, the square root of 0 is 0. So I have my first point. At x equals 1, the square root of 1 is 1. And x equals 4 is the square root of 4 is 2. So here is my parent function. So I'm going to start with the parent function. And then my equation is the square root of x plus 3. So I have a transformation of a horizontal shift left by 3. So I'm going to take my 3 primary points that I have here, and I'm going to shift them left 3. So here, here, and 1, 2, 3 here. So here is my function, f of x. And I'm going to write my 3 primary points down in my table. So I have -3, 0, -2, 1, and 1, 2. Okay, so my next is I'm going to switch my points. The domain becomes the range, and the range becomes the domain. So -3, 0 becomes 0, -3. -2, 1 becomes 1, -2. And 1, 2 becomes 2, 1 for my inverse. So now I'm going to plot my inverse points. So this is 0, -3, 1, -2, and 2, 1. So these points go like this. So this is my inverse. So when I'm looking at these, the function and the inverse should be symmetrical over the y equals x line, okay? And I know I did it right if they're symmetrical over the y equals x line. So looking at that, I can see I got that. All right, now I want to state the domain and the range. Okay, so let's look at what's the domain of my original function. So domain is left to right. So looking at my original function from left to right, I start at x equals -3 and I continue to infinity. So I'm including -3 and I continue to infinity. And my range is from bottom to top. So the bottom is 0 and top is infinity. I'm including 0, so I'm going to use a bracket. So that's for my original function. So now I'm going to look at my inverse. So my domain becomes my range, and my range becomes my domain. So when I know either the function or the inverse, then I know the other one. So my domain of my inverse is now 0 to infinity, and my range is from -3 to infinity. All right, so let's try another one. I'm looking at f of x equals x squared plus 3. My first question is my function 1-to-1? So what I see is if I plot the parent function, I know my parent function is x squared, so that's quadratic, and the plus 3 is a vertical shift of 3 up. So if I'm looking at my function, I have a parabola that is shifted up 3. So 1-to-1 says I could pass a horizontal line down and only touch it once. So if I am going to pass a horizontal line, I can see that I'm going to touch it in more than one place. So my answer would be no. I am not 1-to-1. And I fail the horizontal line test. So do I have an inverse? No. So if I don't have an inverse, then the process is I want to restrict the domain so that I do have a 1-to-1 relationship. So to do that, I want to only look at half of the parabola. So if I don't look at the left half, if I just look at the right half of the parabola, then yes, I would have a one-to-one function with a restricted domain. So I'm going to restrict it starting at 0, and I'm going to include 0 and go to infinity. So now I'm going to graph this. So I'm going to do the same process. So I'm going to switch x and y, solve for y, plot both, and state the domain and range of both. Okay. All right, so starting out, so I have y equals x squared plus 3. I'm going to switch x and y. So x equals y squared plus 3. I'm going to solve for y. So I'm going to subtract 3 from both sides. So x minus 3 equals y squared. I need to undo the squaring. To undo the squaring, I'm going to take the square root. Whatever I do to one side of my equation, I need to do to my other side to keep my equation equal. So I have now x minus 3, the square root of x minus 3 equals, y. So I have the square root function, again, x minus 3. So this means I am moving 3 to the right. So I'm going to start by plotting the parent function first. So my parent function is my quadratic equation. So my quadratic equation, I'm just plotting the right half. At x equals 0, y is 0. At x equals 1, y is 1. At x equals 2, y is 4. So here's my parent function. Next, I'm going to plot the function with the transformation. So the equation is x squared plus 3. So I'm moving 3 to the right. Or I'm sorry, plus 3 is a vertical transformation up 3. So I'm moving everything up 3 y values. 1, 2, 3. So this is my function f of x. And now my inverse, I'm going to get my points from my original function. So my 3 points from my function are 0, 3, 1, 4, and 2, 7. So for my inverse, I'm going to switch my domain with my range and my range with my domain. So now this becomes 3, 0, 4, 1, and 7, 2. So I'm going to switch and plot my points. So 3, 0, 4, 1, and 7, 2. So here is my inverse. And I know if I did it right, if when I'm plotting, if they're symmetrical over the y equals x line. So if I fold my paper in half on the y equals x line, I should have the same thing. Okay, so it looks good. So now I need to state my domain and range. So my domain for my original function. So domain is from left to right. So domain, I start at 0. I'm including 0, and I go to infinity. My range is from bottom to top. So I'm starting at 3, and I'm going to infinity. For my inverse, I'm switching the domain and the range. So the domain is 3 to infinity, and the range is 0 to infinity. Okay? What about, we're going to do verifying inverses. To verify algebraically two functions are inverses of each other, I'm going to show that the inverse and the original function's composition equal x, or I could do it the other direction and start with the function and compose it with the inverse, and the result is x. So again, the x comes from, so the x comes from, I'm not sure. Why is it not doing that? So the x comes from that I'm symmetrical over the y equals x line. Okay. This is where the x comes from. Okay, so determine algebraically whether the two functions are inverses. So I can take the inverse or the function first. So I'm going to say f of g of x. So g is the inner function. So I'm going to take the inner function and put that where my variable is. So this is going to be the square root of x squared minus 2. And then I still have a plus 2 from the original function. So minus 2 and plus 2 total 0. So this is the square root of x squared, which equals x. And that I am looking for is my solution x. So then I say verified, and I show that with a check mark and say yes. All right, let's try another example. Which of the functions is the inverse of f of x? Is it g of x or h of x? So I'm going to solve f of g of x and f of h of x. So I'm going to take g's equation, and substitute that where I have an x. So this is, so I'm going to take this and put this where I have an x. So I have 5 divided by x minus 2 divided by 5 minus 2. So in the denominator, I have some fractions, so I have to have a common denominator. So my common denominator is going to be 5. So now I have 5 divided by x minus 2 divided by 5 minus 2 times 5 is 10 divided by 5. So this is now 5 divided by x minus 2 minus 10 is x minus 12. And then I still have a 5 in the denominator. And the 5 in this denominator is logically equivalent to being in the numerator. So if I flipped and multiplied, so now I have 5 times 5, which is 25, divided by x minus 12. And this does not equal x. So this is g of x is not the inverse. All right, so let's try the second one. So this is where I'm going to take h of x and substitute this where the variable is. So this is going to be 5 divided by 5 over x plus 2. And I have minus 2 still. So plus 2 and minus 2 total 0. So this is 5 divided by 5 over x. So the denominator of the fraction in the denominator is logically equivalent to being in the numerator. So if I would flip and multiply, so this is now 5x over 5. So 5 divided by 5 is 1. So my result is x. So yes, I verified this is h of x. Oops. H of x is the inverse. So h of x is the inverse. Okay, that's the end of the lesson.